All right, I want to finish up sections 5.4 and 5.5 here with just kind of the basic information of logarithms. In the previous video, we had talked about our properties of logarithms. I went over this sheet here with our laws of exponents and logarithms. Again, this is on Blackboard, and if you want to print that, that'd be great. And so now one of the things that we had done earlier in this section was finding values of logarithms. Okay, and in those problems there, I had been using the definition, and that's fine. That's one option that we could use. But now that we've gone over the properties of logarithms, we can consider using those to do calculations as well. So I'm going to find each value here. Now, more specifically, I'm going to be finding values without a calculator, although in the last two parts, I'm going to need a calculator to get the answer there. I'll comment on that once I get there. Part A, okay, we want to find log base 8 of 2 plus log base 8 of 4. Well, if I'm adding two logarithms with the same base, law 1 says that I can condense that to a single logarithm by multiplying the inner terms. 2 times 4 is 8. And so I'm looking at log base 8 of 8. Law 5 on the sheet says that whenever the base and the input are the same, you always get 1. Okay, so log base 8 of 8 is 1. Part B, I've got the ln of e to the negative fourth. Well, law 3 says that powers can come out of logarithms. Okay, so I'll do that. I've got negative 4 times the ln of e. Now, the ln notation is shorthand notation for representing log base e. The ln of e would be 1 since the base and the input number are the same. Okay, so really you're just simply taking negative 4 times 1 is negative 4. The ln of e to a power is always just going to be that power, since the power is going to come out of the calculation and the ln of e is 1. That will always happen. Okay, so like the ln of e to the negative fourth is negative 4, the ln of e to the sixth is 6, etc. Part C, we've got log base 3 of 3 to the 71st. So 71 can come in front of the logarithm, again using law 3. Log base 3 of 3 is 1, since the base and the input number are the same. And so really I'm just taking 71 times 1 is 71. Okay. Another way that you could have done this is you could have used law 6 in the problem. Log base a of a to the x is x. And x in this problem would be 71. Okay, now law 6 is really just kind of a combination of laws 3 and 5. Okay, because that's what I was doing here. I was using law 3 to pull the power in front, law 5 to get this 1. And that's another way to look at where law 6 is coming from. Part D, log base 2 of 8. Well, 8 is the same as 2 cubed. And that's how I'd want to think of 8 here in this problem, because log base 2 of 2 cubed is very much like the last problem I just did, just different numbers. So the 3 can come in front of the logarithm. Log base 2 of 2 is 1. 3 times 1 is 3. Okay, so log base 2 of 8, that's equal to 3. Now, in part E, I want to find log base 2 of 9. In part D, it conveniently worked out so that 8 is a power of 2. Now, 9 is not a power of 2. Okay, so this problem is going to be calculated different from what we saw in part D. In a situation where you can't get the base and the input number to match, you want to consider changing the base. Okay, now the last law on that sheet there was the change of base formula. And I'm going to change the base here to make it a new base. Now when you use the change of base formula, typically you want to make the new base be either base E or base 10. It's not going to matter. I'll comment on that here in just a moment. But suppose I want to change the base to be base E. Okay, well if I'm working with base E, that means I'm working with the natural logarithm. And I'm going to be dividing two natural logarithms here. And 9 is going to go into the logarithm up top. 2 is the old base. That's going to go into the logarithm in the denominator. And so log base 2 of 9, that would be equal to the ln of 9 over the ln of 2. Now the nice thing about changing the base to base e is because I can now go to the calculator and I've got an ln button here. Okay, most calculators have an ln button. Even the cheap $5 Walmart calculators have an ln button. It's just finding it, you know. So, all right, I'll just simply type in the ln of 9 divided by the ln of 2 and hit enter. And I'm getting 3.17. If I go nearest 2 digits, I went out a couple more digits there, that's fine. All right. And by the way, before I did this problem, I probably could have expected log base 2 of 9 to be a little bit bigger than 3. 9 is a little bit bigger than 8, and log base 2 of 8 was 3. So log base 2 of 9, you know, this number at least sounds right if you compare what we did to part D. In fact, it is right, but just an observation there. Now, it doesn't matter what the new base is, but it makes the most sense to be changing the base to be either base E, like I did here, or base 10 is another option. If I change the base to be base 10, then the only adjustment would be, instead of the ln notation, I'm going to have log notation. It's going to be log of 9 divided by log of 2. Well, if I were to type in, I've got log of 9 divided by log of 2 and hit enter, notice how I get the exact same number as I did when it was base E. Okay, that will always happen, actually. And so that's my point, is that it's not going to matter what the new base is. Of course, it makes the most sense, though, to be changing the base to be either base E or base 10, since then you can go to the calculator with those two options available. Part F is going to be a similar deal here, where I'm going to want to change the base. I'm actually going to want to do that twice. Since 6 is not a power of 2 and 19 is not a power of 7, I'll want to change the base on both of these. I'm going to change the base to be base 10, although I could have used base E, that's fine also. Again, the numbers will be the same. So, using the change of base formula, log base 2 of 6, that's equal to log of 6 divided by log of 2, 2 is the old base. And then log base 7 of 19, that's equal to log of 19 divided by log of 7, 7 is the old base. And so now I can go to the calculator here and just type in log, what was it, log of 6, oops, log of 6 divided by log of 2, and then plus log of 19 divided by log of 19 divided by log of 7. Okay, and I'm getting 4.098 roughly when I give the answer there. Oops. Okay. Now, I suppose that I could change the base whenever I want, you know, and I could turn every single problem into a calculator problem, but there's really no reason to be doing that on most of these problems. Okay, if you're familiar with the properties of the logarithms and the definition of a logarithm. All right, so consider that, you know, with when you're handling the calculations there. I just wanted to go through two problems that I thought were some good application problems that are in the book next. So the first one that I wanted us to look at is on page 456, problem 140. I've got that right here. And so it says predicting wind speed. Wind speed typically varies in the first 20 meters above the ground. For a particular day, let the formula f of x equal 1.2 ln x plus 2.3 compute the wind speed in meters per second at a height x meters above the ground for when x is greater than or equal to 1. All right. Part A, find the wind speed at a height of 5 meters. So x is the height, f is the wind speed at that height. So here I just want to simply plug in 5 and then simplify. Okay. If I do that, ln 5 and then times 1.2 plus 2.3, I'm getting 4.2 if we go nearest one digit on that. Okay, the units are meters per second, so basically my interpretation would be to say that on this particular day, if you're 5 meters above Earth, the speed of the wind would be roughly 4.2 meters per second. Part B in this says to graph the function using this viewing rectangle and then interpret the graph. Okay, so if we do that using the graphing calculator, I'm going to hit y equals, I'll clear that out, it is 1.2 times the ln of x and then plus 2.3. Now, they're telling me the window settings here to use. For x, I'm going to go 0 to 20, and the increment is 5. And then on the y-axis, I'm going from 0 to 7, it says, and we'll use an increment of 1 there. If I hit graph, then here's what the curve looks like. Now, I've got a picture of that curve drawn by hand. Now, if I already know what the graph of y equal the ln of x looks like, and we've already looked at that graph, I can use transformations, right? I'm going to have a vertical stretch by a factor of 1.2, multiply the y values by 1.2, and then the plus 2.3 means that you'll shift up 2.3 units. Okay? And that's how I'm getting this graph here. Now, what that means to us is, because it says to interpret the graph, okay, at first the wind speed is increasing, and then it begins to level off. Okay? That's pretty normal for any given day. The speed of the wind is going to vary more, is going to increase more when you're closer to Earth. Okay, that's why planes fly real high in the sky. That's why birds fly real high in the sky, right? Because the wind's not whipping all around like it is when you're closer to Earth. So to me, a logarithmic curve makes sense to be working with in this problem, since the speed of the wind is going to kind of level off there the higher that you are above Earth. Okay, let's take a look at part C. They want us to estimate the height where the wind speed is 5 meters per second. F of x is the wind speed, and x is the height. So I'd want to set the wind speed equal to 5 and solve this equation here for x. If you subtract 2.3 on both sides, 5 minus 2.3 is 2.7, and then 2.7 divided by 1.2 is 2.25. Okay, so I'm looking at ln x equal 2.25, and if I rewrite this into an exponential form, right now I'm in logarithmic form, using the definition, I've got log base e of x equal 2.25. X is my input, e is the base, 2.25 is the y value, and that allows me to get rid of this logarithmic notation here, which is good. So then I can go to the calculator and type in e to the power 2.25. If I do that quick here, e to the power 2.25, oops, I'm getting 9.5 roughly if I go nearest one digit. That's the height, which is in meters, so you're roughly 9.5 meters above Earth, and the speed of the wind is 5 meters per second is the interpretation that we'd make there. Okay, I wanted to look at one more problem on page 481. Page 481. Let me flip there real quick. Problem number 118 I thought was another good one with logarithms. So it says to refer to exercise 117. The lifespan of a sample of sparrows was studied. The equation given here calculates the number of years required for X% of the sparrows to die, where X is a number between 0 and 95. Now in this other problem, you're working with robins. Here's sparrows. Okay, it's a very similar deal. Part A, in this, we want to find Y when X is 40, and then we'll interpret the answer. Part B, we want to find X when Y is 1.5. Okay, so I've got this written down here. In Part A, I want us to find Y when X is 40. So X is 40. I'm just going to simply plug in that number. 100 minus 40 is 60. And then I can go to the calculator and type in 2 minus log of 60, and we're dividing that by 0.37. Okay, and I'm getting 0.6 roughly. Y is the years. X is the percent of the sparrow population that has died off after Y years. So the interpretation of this would be to say that 40% of the sparrow population that was originally there in the area had died off in 0.6 years. Okay, now of course as time goes on, more of the sparrow population that was originally there is going to die off. Okay. Now in part B, we were supposed to find X when Y was 1.5. So here's my formula that was given, and I've set Y to be 1.5, and I got to solve this equation for X. I'm going to multiply both sides by 0.37. 1.5 times 0.37 is 0.555. And then if you add log of 100 minus X to both sides and then subtract 0.555 from both sides, 2 minus 0.555 is 1.445. And to get rid of the logarithm, I would say use the definition and rewrite this into an exponential form. 100 minus X is my input, so that's going to be all alone on the exponential. The base is base 10. 1.445 is my Y value. And if I add X and subtract 10 to the power 1.445, I've got X all alone here. Going to the calculator will give me 72.1% after typing this in. So the interpretation of this part here, part B, would be to say that 72.1% of the sparrow population that was originally there would have died off in 1.5 years. Okay, and again, as time goes on, more of the sparrow population is going to die off than from what was originally there. Okay. At this point, we are now done with sections 5.4 and 5.5. We will be doing some more with some applications a bit later. There is some more to know here, but have a go at these 2 pages. This is the homework that I'd like you to look at from 5.4 and 5.5.